Our final section is 3.23, and this will give us an equation that allows us to calculate the losses from radiation. So here's the figure we've used before when we were talking about losses from heat loss from convection. And we're also going to say, here's this same motor, this totally enclosed motor. And we're also going to see that there are radiation heat losses in addition to the convection heat losses. So, you know, they're both given to us. And, you know, here's the convective losses, and here's the radiant losses here. And so we have an equation, it's our final equation, equation 321, that tells us that the heat radiated in watts is equal to a constant K. And the constant, you can find the constant, it's on page 65. There are these radiation constants that are given to us. Again, this is one of those wonderful things that as an engineer, technologist, and technician, you know, we don't have to derive these, but they are given to us, and they relate a type of surface that is commonly encountered in electrical equipment. You know, these you might think of them as coatings or paintings of particular electrical machines, and you know, it sort of runs through the list there. You know, polished silver and tungsten and oxidized iron and so forth. But in this particular problem, he's telling us that we're going to use the one that relates a non-metallic enamel in table 3B, which is the next to the last one. So what we're doing here, we're looking at this example 318, and we want to calculate the heat loss. So we have to be given the K. The A that is represented in this equation is the surface area of the body. Now we could tell that, for instance, you know, with this motor, that calculation of the surface area might not be the easiest thing to do, but that could be done. And so we could, you know, we could figure out what that might be. Then after we get that information, we multiply the absolute temperature in Kelvin. Well, you know, the difference between absolute temperature of the body and absolute temperature of the surrounding objects. Look at both of those. They're raised to the fourth power. You can imagine this is getting into an area that I'm certainly no expert in, but we can take that expert's information and we can utilize this equation to make some calculations with that. Okay, so you know, he tells us our surface temperature is 60, so we have to convert this to degrees Kelvin. We have the surrounding temperature is 20, so here we go. We've got enough information now that we can work this problem. 5 times 10 to the minus 8, and I'm going to drop the units there. It's watts per meter squared times Kelvin temperature to the fourth power. Imagine deriving that, huh? And then the area that we're dealing with here, let's see, where does this come from? You must have told us that somewhere. I just see a number here, this 1.2. Oh, that was from the earlier, that's right. That was in the earlier problem that it came to us from example 316, where he told us the totally enclosed motor has a surface area of 1.2. So that number came to us from page 64. And then what we do from there is we plug in this 333 to the fourth minus 293 to the fourth. All right, and we take care of that inside. We multiply it by 1.2, then we multiply it by 5 times 10 to the 8th, and we end up with a number of 296 watts. The 296 watts, this approximate value that gives us the radiant heat loss in this motor. So 2 types of losses that we looked at on the same motor, right? We had radiation losses and we had convection losses. And we see that they're really not, not that big a difference between the two of them. Okay, so that's the last section in chapter 3. A lot of good information, a lot of information that we will reference throughout the rest of the course. Sort of these foundations of mechanics and heat that we're going to be able to need to don't need to be expert in, but we at least need to know the terminology and some of the basics there to be able to accurately work with